Hi, my name is Hayden Kaliji, and this is the video section of Project 1, the 2D flow simulation in ANSYS Fluent. So starting with case 1, or sorry, case A, which is the Peisel flow. Um, so our geometry is set to 2D. Uh, we must be sure that the geometry is set to 2D. So I'm going to open up our mesh here. So our geometry is just a rectangle, which is 0.01 meters in height and 1.5 meters in length, which is the 150 times the height as described. So here is basically what our surface looks like. Let me zoom out here. So yeah, this is what it looks like basically. Um, and yeah, like I said, the height is 0.01 meters and the length of it is 1.5. So this is very simply um, our boundary. So let me close this, and now going into our setup, I'm just going to edit this since it is already done. Okay, great. Alright, cool. So in Fluent here, you can see we have our mesh, which we set up, which I had just shown you. So in here, there's quite a few things that we must adjust. So starting with our fluid, mine is named air, although this is set to be water. I just didn't rename it, but it is going to be water throughout all three of the cases. So our density is set to 998.2, viscosity 0.001, which results in a Reynolds number of around 998 with our height and our length values as well. So then if we go to our boundary conditions, so we have all four sides, so the top, the bottom, the inlet and the outlet, all specified. So our bottom wall here in case A is completely stationary, non-slip, and it is the same for the top wall. Our inlet is a velocity inlet, outlet being a pressure outlet, and the velocity on our inlet is 0.05, I believe. Yes, 0.05 meters a second. And then, of course, our outlet, the gauge pressure is 0. So, like I said, both of the walls are stationary. So I will initialize this. We run this in hybrid. Okay. And now we can run the calculations for this to show our residuals. Alright, cool. So that looks pretty good. Yeah, so that looks good. So once we have initialized and calculated after changing all of our parameters here, and then we are given our residuals, so we can't really tell much from these provided residuals. We are going to have to plot this and look at the velocity contours and vectors to really confirm if it's Peisel or not. So we can just minimize this, and in results here we can right click and update these. Perfect. So now we can open up our results section. So in here, of course, this has already been done. So this already has the contours and the vectors. I'm just going to go ahead and delete both of these, as well as the end and midline, to show how I do it myself, or how you would do it. So starting, see, here's our sketch. We can go up here, click vector. I'm going to name this vector, or sorry, velocity vectors. Click enter. Now in here, all domains is okay. Vertex, basically all this stuff can stay the same. Color, we're going to change this to divergent blue, yellow, red. Symbol, I'm going to change this to be 0.1. 1 will give you a symbol that is way too large, and it will be completely obscure. You won't be able to tell anything. All of this stuff looks good, so now we can just apply this. Oh, whoops. Location. Set this to symmetry. There you go. Cool. So, zooming in, you can see our velocity vectors. Looks pretty good. Oh, and as far as the legend goes, if I go here to default legend view, I just click this. I just turned it to horizontal, increase the size a little bit, change some things. Whoops, did not mean to set the position to that. Whatever, we'll just leave that. So now, for the contour, same thing, just go to the top, and we'll click contour and name this velocity contours. Okay. So number of contours, uh, typically you could just do a high number. It'll give you a nicer gradient. You can do something lower, and it will be quite obvious, the change, but just go with something higher. It doesn't really hurt. So location, we can do this as symmetry, and I'm actually just going to hide the velocity vectors for now. Same thing, all domains, pressure. Make sure this is velocity, range, global, contours, all domains. Okay, apply this. I'll just give it a second because our number of contours is so high it might take a moment. Perfect. So here is our velocity contour of our pi cell flow. Okay, you can see how it looks in the beginning with the pressure gradient. So now we can make the actual graph. So we can go up here to location. Let's see if it lets me. And we'll throw in a line. We can name this midline. This will be our midline point for our graph, since we need to find the velocity profile at the midline and the end line. They should look pretty similar as well. So we'll make a midline, 0.1. So this is our x, y, z. Z we're just not going to touch. So we do want this to be center, which is 0.75, half 1.5, right? And for this, we'll do 0.75. or we'll just start it at 0, and it'll go up to the top, which, like I said, our height is 0.01. Now we'll click I. Okay, and now if we zoom out, we should have a midline here. There you go. Cool. So now we'll do the same thing. Line, but this time we'll call this one end line. Okay. So same thing. Our x is, we're gonna actually do right before the end, 1.49. It will be relatively the same. Same thing, 0.1. Then apply this, and we should see if it's at the end here, which it is. Perfect. So now that we've got this, we can make our actual plot. So we're going to go up to Insert, Chart. We can call this Velocity Profiles. Oops. There's already one called that since I've already done this here. Actually, I'll just here and delete it. There you go. Okay, so like I said, Insert, Chart, Velocity Profiles. So we can just name the same thing. Profiles. So we'll do this in as a line type. Data series will add both of our series. So let's call this guy midline. Our location, of course, can be the midline. Add another. Do our end line. Location being end line. Our x-axis, we're going to change this to be velocity u, and our y-axis should just be y. And then our range will be from 0 to our height, which in my case 0.01. We can apply this now, and here is our velocity profile for the Pycelle. Looks pretty good, basically just a parabola. And this is basically how it should look. Oh, whoops, I didn't realize I changed that. But yeah, this is Pycelle. So now I can go ahead and move on to part B, which is the Couette flow. Okay, cool. So now for the Couette flow, it's the same exact setup, same exact mesh, same geometry and all that. The only difference is with our boundary conditions. So we can go ahead and open up this guy here. I'm not going to go through the mesh and geometry because, like I said, it's exactly the same. So, okay, so now that we're in, things are pretty similar. The fluid, of course, is exactly the same. We don't want to change that at all. Our boundary conditions, however, those have changed a little bit. So our bottom wall is going to be just stationary, same thing, non-slip, stationary. Our top wall, however, will be moving with a velocity of 0.05 meters a second in the positive x direction. That's why this is just positive. Make sure to set the motion to absolute, moving wall. Okay. And now for our inlet, instead of it being a velocity inlet, I had to do it as a pressure outlet, and this was because I was getting a pressure gradient that was not giving me a Couette flow. So in my case, the inlet is set to a pressure outlet as well as the outlet. Like I said, top wall is moving 0.0, or sorry, 0.05 meters per second in the positive x direction, and our bottom wall is just stationary. So it's basically the same exact thing for this. We can initialize and then go ahead and run calculation. Okay. Cool. Here's our residuals. So now we can go in and do the velocity contours and vectors and stuff. All right, so we'll open this. All right, same thing for this. I already have all this stuff made, but it's literally the identical process, exact same thing, even down to the legend. Everything is the same. But this is the velocity vectors for our Couette flow. As you can see, uh, the peak velocity is at the top where the wall is moving, of course. And then here's our contour, right? And now for our profile's not here, so I'll actually just make this really fast. So insert chart, velocity profile. Here's our Couette flow. So as you can see, it's linear as compared to the velocity profile of our Pycelle flow. And of course, this is due to the wall at the top, which is moving. See, I accidentally messed this guy up. Alright, so that is our Couette flow. And now for a combination of the both. Okay, so for the combo of the two, once again, same geometry mesh, I would just go in and show you the difference in the setup. Alright, so once again, same material, water, the 998.2 for the density, the 0.001 viscosity. Our boundary conditions are relatively similar. So our bottom wall here is stationary, just like in the Pycelle flow. Top wall is moving in the positive x by 0.05 meters per second, just like in Couette. Our inlet is a velocity inlet, like in Pycelle. Outlet is pressure outlet, just like in both. And those are really all of the differences here. There isn't really much. So we can go ahead and initialize this guy. And then run the calculation. Okay, this looks good. So We can now, the same thing, update our results. Oh, and this might be one thing I forgot to mention, but under here, under modes, it is set to laminar. That is important. Everything will be wrong if you do not do that, so. Okay, this is updated. Let's open this now. Close Fluent. Alright, so once again, I have the contour and the velocity vectors already made, so here I'll zoom in on this. So here it is. As you can see, it's not like our Pycelle where it's perfectly parabolic, and it's not, or not perfectly, but it's not parabolic, only slightly. And it's not like our Couette where it's a little more linear, but it's actually a combination of the two where, you see at the bottom how uh, it's got a little more curvature, and then at the top it has a little less as it um, because of the wall at the top, which is moving. So here's the contour as well. Here, let me move this. Start. So you can see, and it's basically the same all the way down. And then it's the same thing with the chart. It won't show it, so I will just go ahead and make it really fast. Once again, call this velocity profiles. Line. Then end line. Zero, 0.01. I can go ahead and apply this, and here you go. And now I know it's very hard to see, um, but the midline is there. It's just so similar. It's basically identical, so it's hard to see. You could offset it to make it a little easier to see, but I didn't think that was necessary considering you can see it's there in the legends, um, and we know that they should be pretty similar. Uh, but that is the velocity profile for the Pycelle Coet kind of hybrid there. Um, and yeah, this has been the video for Dr. Osbay's project number one, the 2D simulation in ANSYS Fluent. And thank you.